Hello all. In today's session, we'll talk about the most important network hyperparameter which is used in artificial neural networks called as activation function. This is used in each node of the hidden layer which tells which nodes are active. So when we are building a neural network, one of the main design decisions what we need to make is what kind of activation function should we use for a given task. Now, what are activation functions? These are referred to as transfer functions or nonlinearities because they transform the linear combination of a weighted sum into a nonlinear model. That is, activation function converts linear model into a nonlinear model. Now, why nonlinearity is important? Because linear models can capture relationships where input and output are directly related. But what if you don't have any direct relation between input and output? That is, what if my data set is non-linear? In such cases, neural networks will introduce activation functions which makes the model non-linear. An activation function is placed at the end of each perceptron to decide whether to activate this neuron or not. So depending upon the output of Wx plus B, activation function decides whether to activate that particular neuron or not. The purpose of activation function is to introduce nonlinearity into the network. Without it, a multi-layer perceptron will perform similarly as that of a single perceptron model. Activation functions are needed to restrict the output value to a certain finite value. Example, what we have done previously was step activation function whose value ranged between 0 and 1. So introducing nonlinearity in a model will allow to capture and represent complex patterns. These are different types of activation functions used. We'll go through one by one. The first one is linear activation function. Linear activation function, also called as identity function, indicates that the function passes a signal through unchanged and the equation is given as z is equal to wx plus b. So the composition of two linear functions is also a linear. So unless and until we introduce non-linearity in the neural network, we cannot compute any function no matter how deep our neural network is. So to understand this concept of introducing non-linearity or not using such kind of linear functions, let us look at the graph here where I have used w value as 4 and b is equal to 0 so that z is equal to 4x. This is the graph for z is equal to 4x and its corresponding derivative is here, which shows that the derivative of a linear function is always constant. So in such cases, it will slow down the gradient process when we are dealing with backpropagation algorithms. Coming to the second type of activation function, binary step function. Binary step function ranges between 0 and 1, which we have already discussed. If wx plus b is less than or equal to 0, output is 0. If wx plus b is greater than 0, then the output is 1. That is, it will classify, it is used for binary classification. It will classify as yes and no, spam or not spam, pass or fail, and so on. Coming to the third type, sigmoid activation function. It is used to predict the probability of two classes. Step function will find whether yes or no, whereas sigmoid function will find the probability of category belonging to S and probability of that particular category belonging to no. Probability of a student passing in the exam is 80% and probability of student failing in an exam is 20%. Such type of probabilities of two classes can be done using sigmoid activation function, and its probabilities ranges between 0 and 1, and it is called as a S-shaped curve because the equation for sigmoid function is 1 by 1 plus e power minus z, and this is the graph for sigmoid function 1 by 1 plus e power minus z, and the graph is in the form of S shape, hence you call it as a S-shaped curve. Fourth type is softmax. Softmax function is a generalization of sigmoid function. It is used to obtain classification probabilities when we have more than two classes. Sigmoid function will find the probabilities when we have two classes, and if I have more than two classes, then I make use of softmax activation function. This is the equation e power xj by summation of e power xi. What you notice here is the softmax function will transform the input values to the probability values ranging between 0 and 1. That is 1.2 got transformed to probability of 46% or 0.46. 0.9 got transformed to 0.34 and 0.4 got transformed to 0.20. These are the probabilities which are ranging between 0 and 1, and make a note that summation of all these probabilities will be equal to 1. Next, fifth type of activation function used is tanh activation function. Previous activation functions what we have discussed, that is step, sigmoid and softmax, their values range between 0 and 1, whereas tanh value ranges between -1 to 1, and its equation is e power x minus e power minus x by e power x plus e power minus x. One of the drawback with this sigmoid and tanh functions is that if these x or z values are very large or very small, then the gradient will be approximately equal to 0, which will slow down the gradient descent process, which will be used in backpropagation algorithms. So to avoid this drawback, that is gradient getting closer to 0, the second type of activation function which was introduced was ReLU activation function. Before moving on to the ReLU function, we'll just look into the graph for tanh function, whose equation is e power x minus e power minus x by e power x plus e power minus x. So to avoid the drawback, we have introduced another activation function called as ReLU, which is nothing but rectified linear unit activation function, which activates a node only if the input value is above 0. Equation is given as max of 0, x. You can see in the graph, if the values are greater than 0, then it will be equal to x, and if the values are less than 0, and it will equate those values to 0. So if the input is below 0, the output is always 0, and if the input is higher, then it will have a linear relationship with the output variable. This graph shows linear relationship with the output variable. Coming to the next, leaky ReLU. Disadvantage of ReLU is, if x value is, what is the equation I have, max of 0, x is for ReLU. If x is negative, then the derivative of this function will be close to 0. You can see in the graph here, for all the negative values, derivative is close to 0, so which will slow down the gradient process. So to avoid that, the other the other activation function which was introduced was leaky ReLU, rectified linear unit. So it works better than ReLU. So instead of 0, x, a small negative slope has been introduced here. Instead of 0, it has introduced a small negative slope of around 0.01. We can try different values as 0.1, 0.02 and so on. You can see in the graph that when the values are negative, a small slope which is 0.01 is being introduced. So this is just the summary of all the algorithm activation functions what we have seen earlier. So this is the end of today's session. In the next session, we'll start with the different optimization algorithms. Thank you.